Hello, everybody. Sorry, I'm a couple minutes late here. I had making some videos and got lost track of time just a tiny bit. So let's get things going here. Back, let me close a few things. Welcome to class. Let's see. What was I going to say? Oh yes, of course. 1 second. So here is the attendance link. Please go fill it out. You're going to do this every class, so just get used to doing it. You might even want to bookmark it so that you can do it each time. Definitely not. Turn on your video if you want. Oh, I need to get some water. 1 second. Sorry, a little behind the ball today. Sorry about that. Okay. Let's see. Let's open the window here. Top here. Great. I also wanted to mention, I think a couple of you sent me some emails asking for some content. I just literally made those videos right before class, and I haven't had a chance to post them yet, but I will certainly post them right after class so that you can all see that stuff. We could probably do it while we're doing class, but I'm not that good at being multitasking, so let's see. Oh, else I should pin my video. Sorry. Pin my video. There we go. Sorry, Martha, you were big on there for a minute. You might be big on the video that gets posted. Sorry, you'll live. So you guys have any? So I should actually say one more sec. Apologies. Where's my email here? For I'm going to butcher your name. I'm sorry, Nirjana. I definitely made a video answering your question, which I'll get posted. And Martha, I did make a video answering your question as well, and I'll get that posted right after class. And then I saw that Merckx sent you guys all a quiz review sheet. We could definitely address some of that if you want to. But I should ask, are there any questions you guys have that you would like to see get answered? You can put them in the chat. You can say words with your microphone. Either way is fine. I'll give you guys a minute.
I just had a question about where to go to access the videos that you make.
Oh, sure. So you should be, so if you go to Canvas, in fact, let me share my screen. Canvas. So, sorry, just 1 sec. Oops, there we go. So if you go to Canvas, here's my Canvas with all the various classes. But specifically, if you go to Co-16B, which is what I've called it. Also, by the way, just saying, you guys, if you want, if it's easier for you on your own personal Canvas, you can change the color of things, and you can also change the names of things. If you click on this little 3-dot thing here, you can pick any color you want, right? You can change it to that color or that color, and then if you close it, it'll actually change colors. It should change colors. No, it's not. Fine, don't change colors. Oh, you have to click apply, right? So you can totally change the color if you want. And change it back, and you can change the name. Right, so if you go right there, you can change the name to whatever is easiest for you to read. If that makes it easier for you to navigate through your dashboard, I highly recommend doing it. Co-16B. So if you're trying to access the videos, one way you can get there is just by clicking on the modules tab over on the left here. And then you should see links to all the videos. So this part here is just the class video. So what we're recording right now will get posted on YouTube, and there'll be a link to it here. And there's also the videos I've made. So like if you want to go look at the video I made on implicit differentiation, you can click on this. It should take you to YouTube, and there's my video right there. Great, looking good, video and video. So you can pause that. But then you can also, I believe, yeah, I don't care. If you click on me, maybe, I don't know. I don't know what this looks like from the student perspective. If you look at the playlists over here on the left, there's a Math 16B playlist, and that should have all just the videos that I've tagged for 16B. So that should be how you can access things. That help? Yeah, no problem. Let's stop sharing the screen. Yeah. Okay. Other questions you guys might have? I should actually say, before you get going, I haven't graded your quizzes just yet. I will try to get those graded by the end of the normal day today. What I will say is once they're graded, it'll just show that you've gotten full credit. So if you actually want to see the feedback, you're going to have to go into Gradescope and look at the comments I've made for each question, because although all the comments will be like, you're going to lose 0 points for each comment, there are still things I'm saying in there to help you understand what you've done correctly or incorrectly. So you should definitely go look at those once they are graded and see kind of what feedback there is to see. All right. So what do you guys want to talk about? Antiderivatives. All right, good. You got it. Great. I love it. Sure. Cool. Good stuff. Okay. Where's my blue pen? Okay, good. Okay. If you think of something else, you definitely should chime in. Cool. All right. So let's start off with the first one because it's actually just an actual problem. So I'm trying to solve natural log of x plus the natural log of x plus 6 equal to 0. All right. And so when you're trying to solve a logarithmic equation like this, one of the things you almost always have to do is combine all the logs together on each side so that you just have one logarithm. So I really want to write this as the natural log of x times x plus 6. Right, when you have logarithms added together, you can multiply their products and write it in one logarithm. And then still equal to 0. And then I'm going to rewrite this equation, right? This is really log base e of some stuff equal to 0. I could actually even write it that way if you really want. But then when we rewrite this as an exponential equation, e is the base, 0 is the power, and it's equal to, I like this, e to the 0 is equal to x times x plus 6. So then we actually have to solve this quadratic equation. Right? We've really got 1 equal to x squared plus 6x. I've got 0 equal to x squared plus 6x minus 1. Now, if they were nice, they would have written a problem where this factors. This definitely doesn't factor, right? There's no numbers that multiply to -1 and add up to +6. So if it doesn't factor, you end up having to use the quadratic formula. So my A is 1, my B is 6, my C is -1. My solutions are x equal to -b plus or minus, that's interesting, the square root of b squared minus 4 times a times c all over, what do we got here, 2 times a. Sorry, which is 1. And we should try to simplify this, people, because we really actually kind of need to know about it. So let's see, I've got -6 plus or minus the square root of 36 plus 4 is 40 all over 2. Often I would leave it like this, but here I actually need to know a little bit more. So square root of 40, I can definitely pull out a square factor. 40 is 4 times 10. And the square root of 4 is just 2. So this 40, which is just 4 times 10, that 4 comes out of the square root, and the square root of 4 is 2. This is -6 plus or minus 2 times the square root of 10. all over 2. And then each thing gets divided by 2. So I end up with negative 6 divided by 2 is negative 3 plus or minus the square root of 10. Okay.
Wait,
so what's that?
Where did you get negative 6 from?
Because the formula for the quadratic formula is it's right, it's negative b plus or minus the square root.
Oh, okay.
All over 2a. Now here's the thing with logarithmic equations. Sometimes your answers aren't actually your answers. Sometimes you get what are called extraneous solutions that are not in the domain of the original expression. So if you recall, for a logarithmic function, the insides of the function has to be positive. So if I look at this, here looking at this, I see that, oh, x has to be greater than 0. And here, x plus 6 has to be greater than 0, meaning x has to be greater than negative 6. So in this particular problem, both of those things have to be true for our solutions. And I can see that it's definitely not true for at least one of them, right? Negative 3 minus the square root of 10 is definitely negative. So it's not a solution. It's what's called an extraneous solution. So this is because, right, if I plug this in here, I would get a negative number. If I plugged it in here, it would also be negative, but once it's negative somewhere, we don't really care where else it's negative. It's going to be negative. It's going to be not a solution. So if you can see that whatever number you've got here makes your answer negative, or sorry, makes what's inside the logarithm negative, it's not an answer. It's not a valid solution. So this one is not a solution. What about negative 3 plus the square root of 10? It's definitely bigger than negative 6, but is it positive? Is negative 3 plus the square root of 10 positive? Ooh, I should make you guys practice using the yes and no. So you can definitely, anytime you want to say yes or no to a question, you can definitely hit the, if I ask you something, you can, oh, my mouse just stopped. You can hit the no or the yes, right? So if you want to do that, that's great. If you want to just say words, you can. What do you guys think? Positive or negative? That's not a good yes or no question. Is it positive? Yes. And we know it's positive because the square root of 10 is definitely bigger than the square root of 9, which is 3. So this is definitely positive. And so since it's positive, it works there, it works there. So this is our only solution to this equation, the negative 3 plus the square root of 10. For those of you that might have just joined, here is the link to the attendance document again. Please get used to just filling this out as soon as you see it. All right, good question.
How did you get from ln to log? Is ln equal to log base e? And then did you do that to the 0 too, or like?
So I didn't do that to both sides. What I did was I rewrote this equation as an exponential equation. So actually, can I do another example? I think that'd be good. Do I have a good one? Yeah, I have an all right one. So just to kind of answer your question, we exactly did the thing where we just rewrote this, right? Just like, sure. Just like more easily, we know that log base 2, this is my favorite example. I will use this all the time when I talk about logarithms. We know that log base 2 of 8 equals 3. Right? Because again, when you're finding a logarithm, you're really answering the question, this base to what power is equal to that value? Oh, 2 to the third is equal to that power. But you can also rewrite it as the base to the power is equal to that stuff right there. So that's all I did. I took this logarithmic expression or equation and rewrote it as the equivalent exponential equation. So let me do one more example. I'm going to make something up, which means it might not come out great. I'll make it not too terrible. Let's say we've got log, let's see, what do I answer be? Sure, I can make that work. Log base 2 of x plus 5 plus log base 2 of, sorry, I have to think for 1 second. That's dumb. Sorry. Sure, we can do that. No, x minus 1. Yeah, that works. I have to think for a second, apologies. Okay, I think that should work just fine. Let me just double check in my brain. Yeah, okay, good. So we're gonna do this one. And again, for the first step to solving equations like this that are logarithmic is to combine all your logarithms. Oh, I didn't solve it in my head. I made it up in my head. I said I knew what I picked the answer to be, and then I plugged in that value for x to make sure that it was right. I didn't make up the problem and then solve it. I had an x in mind and was like, oh, I'm going to make x equal to that, and then that'll be the answer. So just so you know, I was like, oh, I want x to be equal to 3 to be my answer. So then I plugged in 3 and I said, oh yeah, log base 2 of 8 is 3. Log base 2 of 3 minus 1 is 2. Log base 2 of 2 is 1. And then 3 plus 1 is 4. That's really what I did. But we don't know that's the answer, so let's solve it. So I'm going to combine these two into one logarithm. So we've got log base 2 of this times this, since it's plus. If it was a minus, it would be that divided by that. X plus 5 and then I'm going to rewrite this as an exponential equation. So here's my base. It's going to get raised to that power. And it's going to then equal what's inside there. So 2 to the 4th is equal to x plus 5 times x minus 1. One of the common mistakes I see when people do questions like this is they kind of forget about this raising to a power part, and they just end up saying this stuff in here is equal to 4, which is totally not correct. So then I'm just going to solve this, and it's usually going to be a quadratic equation. So here, 2 to the 4th is 16. Multiply this out, you get x squared plus 5x minus x minus 5, right? X squared, 5x minus x minus 5. And then bringing everything to one side, I'm going to get 0 equal to x squared. 5x minus x is 4x. And negative 5 minus 16 is negative 21. And hopefully, I should say not hopefully, the general thought is that hopefully this thing factors. So I will look to make sure and factor it. No. Oh, yeah, totally. So here, I can factor. I'm trying to multiply the negative 21 and add it to positive 4. That's looking like x plus 7 times x minus 3. So I should ask, what are my possible solutions? Well, here I'm going to get x equal to what?
Negative 7.
Thank you. And somebody else tell me, what do I get from here?
3.
Yeah, totally. But then you have to check and make sure that they are actually solutions in the domain of the original expression. You have to go back to the very first expression, which was this, and plug in 3. If I plug in 3, I don't actually care that it works. I just care that it's the inside the positive. So if I plug in 3 here, is 3 plus 5 positive? Of course. Is 3 minus 1 positive? Of course. So we're good. 3 is good. Then I check negative 7. Now I will tell you, sometimes negative numbers work because you have different things here that make it negative. But if you plug in negative 7 here, is negative 7 plus 5 positive? No. So we're done with negative 7. It's not a solution. I want to point out though, if you're not careful, you might think it is. Because if you plug in negative 7 here, it would totally work out just fine. Negative 7 plus 5 is negative 2. Negative 7 minus 1 is negative 8. And negative 2 times negative 8 is positive 16. So if you plug it in any further step down, you might accidentally mistakenly convince yourself that it is a solution. But that's why you have to look back at the original expression that, oh, if I plug it in there, it doesn't work. So that's what's going on with that kind of question. Let's see, what else? I see people asked a couple other things. You can't see the link. Let me, oh, you know why? It's because I accidentally, someone sent me a private chat and then I accidentally responded to them. So let me fix that. Apologies, everyone. Here is the link now. If you see me not responding to your chat question, just go ahead and speak up. I don't always see all the things because my chat box isn't very big, so I'm trying to see all you guys. Let's see. So what else did you guys ask about? That's about logarithmic functions in general. Caitlin, do you want to expand on that a little bit? Like, I'm not exactly sure what you mean. Like derivatives of logarithmic functions, or how to like put them together. Okay. I see someone else asked about inverse problems, verbal problems. I assume you mean like word problems. So I'll come back around to logarithms. So inverse, I think it's inverse problems or inverse functions. Let's see, inverse, sorry, it's hard to read all the things. Inverse functions, okay. Okay, good, glad to see that, Kayla. So let's talk about inverse functions for a minute, and then, so I'm definitely kind of holding off on answering the antiderivative questions because that's kind of like the next thing. So once I kind of address all the little other questions, then we'll kind of move toward antiderivative. But the question that Fernanda just asked, finding an equation given the derivative, is the same question as finding the antiderivative. So let's talk about inverse functions for just one sec. I'm not exactly sure what you guys are having to do with inverse functions, but I can talk about the process for finding an inverse function if that's kind of what you're asking about. I don't remember who asked that. Not that it really matters who, but so for example, let's say I wanted to find the inverse function for, let's see, how do I want to do this? I'm going to do two different examples. Okay, so let's look at this one first. So let's say f of x equal to 3x plus 5 over 2x minus 1. There's a nice function. And when I think about inverse functions and functions, what I usually think about, the kind of the most salient piece of information in my mind is that inverse functions and functions have the domain and range interchanged. That's something that's always true because, well, think about it. How do we find an inverse function? We find an inverse function by interchanging x and y. But the domain is all the things x is allowed to be, and the range is all the things y is allowed to be. So by interchanging x and y, you're interchanging the roles of the domain and the range. So looking at this one, I can see that the domain is, well, x can't be 1/2, right? If I set 2x minus 1 equal to 0 and I exclude that, I see that 2x can't equal 1, x can't equal 1/2. So that's my domain. And we might as well go for it. I can also see the range here. Now this specific type of function, where it's a linear function on top and a linear function on the bottom, you can always see that the range is going to exclude the one value that's the horizontal asymptote. So this function definitely has a horizontal asymptote at 3/2. And the way we know that, I know it might have been a while for some of you, but the way you know that for a rational function, which this is, it's a polynomial divided by a polynomial, if the degree on top and the degree on the bottom are the same, then the horizontal asymptote is the quotient of those leading coefficients. So just as a quick aside, let me ask you guys, I'm going to erase this one just a sec. If my function was something else like this, like 4x to the 7th plus x squared minus 2 over 5x to the 7th plus x to the 6th plus 2x cubed plus 1, looking at this rational function where the degree on top is 7 and the degree on the bottom is also 7, what horizontal asymptote would this function have?
4/5.
Exactly, right? Because the degrees are the same, you get the quotient of their coefficients there. Now, another thing to be aware of is that doesn't always mean that that number isn't in the range. A function can totally cross its horizontal asymptote if it needs to. This one doesn't. In fact, I can totally graph this one for you before we start finding the inverse. this function exactly looks like this. I've got a vertical asymptote at 1/2. So there's 1/2. I've got a horizontal asymptote at 3/2. I would have a y-intercept. If I set x equal to 0, I get +5 divided by -1, so I get like -5 down here. There's my y-intercept, -5. And I get an x-intercept. If I set the top equal to 0, I get 3x equal to -5, x equal to -5/3. That's like over here. So this function looks like this. It's going to go down this way. It's going to go up this way. It totally doesn't have 1/2 in the domain. Totally doesn't have 3/2 in the range. Another way I'm going to say this, just because I think it's kind of important to see this, is you could also see that if I set this equal to 3/2, there isn't any solution, right? If I cross multiply 2 times 3x plus 5 equal to 3 times 2x minus 1, I get 6x plus 10 equal to 6x minus 3. The 6x's cancel. I get 10 equal to -3, which isn't true. So that's another way to see that 3/2 is not in the range here. So all the things I've just said here are nice, but they're all kind of the most complicated way to think about the range. They're good ways of thinking about the range, but the way you really want to think about if someone asks you to find the range of this function is say, oh, I'm going to find the domain of the inverse function, because that's kind of the most straightforward way of finding a range. And the reason I'm saying that is because that's kind of one of the most typical things we do with, I take that back immediately. It's one of the things we do with the inverse function, but there's lots of things we do with inverse functions, so I should kind of hold my horses there. So to find the inverse function, you usually use y instead of f of x. So I'm going to have that, and then we interchange x and y. So I'm going to have x equal to 3y plus 5 divided by 2y minus 1. So the one y you had becomes x, and every x you had becomes y. And then, so those are the easy steps, right? They're kind of like nothing steps, really. But then the hard part is actually solving for y. So if I solve for y, let's see, I'm going to get, so I'm going to multiply both sides by that. So I'm going to have 2y minus 1 times x equal to 3y plus 5 divided by 2y minus 1 times 2y minus 1. And the whole reason I multiply by 2y minus 1 is to cancel the denominator. Because I really, really would prefer not to have to work with the denominator. So that's what I do. Then on this side, I distribute the x. So I have 2y times x, which I usually write as 2xy. We typically write things in alphabetical order or lexicographic order if you want a nice long word to say alphabetical. And then x times -1 is minus x. On the right-hand side, I just go ahead. Whoever's trying to say something, I'm not quite hearing you. I'm going to continue on, but if you have something, feel free to chime in. So that's what I get. And then I'm trying to solve for y. So I'm going to bring all the terms that have y's in them to the same side, and all the things that don't have y's in them to the other side. So I'm going to bring everything with a y to the left. I have 2xy minus 3y. Bring everything that doesn't have a y to the right. So add x over here and get x plus 5. Finally, factor out a y, which is why we brought all the things with y's to the left-hand side, or whichever the same side, so that we can factor out a y from all of them. So I've got y times the quantity 2x minus 3 equal to x plus 5. And finally, we can solve for y and get y equal to x plus 5 divided by 2x minus 3. And that's my inverse function. F inverse of x equals x plus 5 divided by 2x minus 3. And notably, this inverse function, I can see that x equal to 3/2 is not in the domain. So here's the domain, right? X cannot be 3/2. Because if you plugged in 3/2, you would get 0 in the denominator. So x not being able to be 3/2 for the domain here means that for this original function, which we already knew, 3/2 isn't in the range. So this function here has a range that is everything except for 3/2. No problem, no problem. All right. So, trying to think. Yeah, we should do one more. There's one other thing that probably won't come up, but occasionally it comes up, so I'll just mention it here. I feel like it's more of any question. No, I think that's enough actually for domain and range. I think I'm gonna yeah. I have another idea. Maybe I'll make a short video if you guys want another example. But yeah, let's look back here. So, sure, antiderivatives. I mean, we should definitely talk about antiderivatives. I just want to see. And then I see, so you said verbal problems. If you have an example of a verbal or a word problem, that'd be great. Why don't you think about that? While I'll start talking about, oh, I know, I had a, oh no, yeah, I did have a thing. I have a handout that I will post on Canvas if we don't start talking about it. I'll post it either way. But yeah, that might actually use, I'm gonna turn on the document camera because I might use the document camera. So antiderivatives. I know we talked about them a little bit last time. And the idea for an antiderivative, actually, I feel like, I feel like Fernanda kind of summed it up nicely here. She wrote finding an equation given the derivative. And that's kind of exactly what an antiderivative is. Like, oh, I know the derivative. I want to know what function that derivative actually came from. So for example, if I had a function, so unfortunately our notation for this isn't nice until we start talking about integration. So for the moment, we kind of have to use funky notation. So typically people either do this by saying, I'm going to give you the derivative and then ask for the original function. Or they're going to say, here's the function equal to something. And they're going to ask, what is capital F of x, which is our typical notation for an antiderivative. So if someone says here's a function and then they ask what the capital letter function is, they mean find the antiderivative. They might not have said those words, but that's definitely the meaning behind it. All right, so we should do an example here. So let's look at something that I think is moderately straightforward. X cubed plus secant x tangent x. And at least at this stage, well, in fact, that's not true. I definitely saw, I forget which teacher, I'm pretty sure it was Merckx, has started talking about U substitution a little bit. Is that correct? Yeah, okay. So we're definitely gonna have to move towards that probably today, because again, I know we only meet twice a week, which is kind of a bummer. I prefer meeting 3 times a week, but that's what we got. So if we don't talk about that enough today, I'll definitely make some U substitution examples. And in fact, that's what the handout I have is about U substitution. So we'll talk about that. All right, what am I doing here? Oh yeah, I want to find the antiderivative. So if you're trying to find an antiderivative, if something looks like a well-known derivative, like secant x times tangent x, I know that secant x times tangent x is the derivative of secant x. So I know that the antiderivative here is, so we have the anti-power rule. So for any power of x, except for x to the negative first, the antiderivative of x to a power is just x to that power plus 1 divided by that new power. And then I know the antiderivative of secant x tangent x is secant x. But really that's based on my knowledge of derivatives, right? So I want to remind you right now, it is really important that you are confident in all your differentiation abilities. You should be able to confidently differentiate any trigonometric function, any exponential function, any logarithmic function, any power of x. I know we just learned exponentials and logarithmic functions, but they're going to come up. So to be good at anti-differentiating, you have to be good at differentiating. So we're going to practice those. I'll probably ask more of those on the next quiz that I give you guys. I'll try and post up. I'll probably start posting the quizzes hopefully before Monday and give you more time to work on them if you want more time, or at least a larger window to do it. So it's not just on Monday. I feel like just on Monday might not be excellent. So I'll do that differently this week. Oh, and then of course, plus c. So here I've got f of x equal to x to the 4th over 4 plus secant of x plus c. Sometimes people give you an initial condition. So they might say, what is f of x? And then they give you some additional information. Given, say that f of 0 is equal to 8. If it hasn't come up yet, it will definitely come up in the future. And it's not like it's a hard thing to figure out. How did I get the first term of the function? You mean the x to the 4th over 4? I'm not sure exactly what you're asking, Melissa. I'll just say, so the way I got the x to the 4th over 4 is I'm using essentially the backwards derivative rule, right? I know that the derivative of something like, I'm gonna use a different power, like x to the 6th. I know that I multiply by 6, and then after multiplying by that power, I subtract 1 from my power to get 6x to the 5th. To undo that, right, so if I want to find the antiderivative of 6 to the 5th, first of all, I know the antiderivative of 6 to the 5th is x to the 6th. And I'm going to remind you guys often, the whole relationship between derivatives and antiderivatives is that they undo each other. If you differentiate this to get this, you anti-differentiate this to get back to this. So if I want to find the antiderivative of 6x to the 5th, so if my derivative is 6x to the 5th, the way I find the antiderivative is, well, I need the power to be 1 greater. So derivatives of polynomials or derivatives of powers of x always make the power 1 less. Antiderivatives have to undo that, so they always make the power 1 greater. So the derivative of 6x to the 5th is, sorry, the antiderivative of 6x to the 5th is 6x to the 5 plus 1. But then I have to divide by 6, which is what my new power ends up being. So that's how that's working. And then there's a plus c. Yeah. And then the secant is just, we know the derivative of secant is secant tangent, so we know the antiderivative of secant tangent is secant. Back to this question though, if I knew that f of 0 was equal to 8, the whole, when someone tells you something like this, that f of 0 equals 8, or f of 1 equals 2, or f of something equals something, what this means, where red pens go, there's red pens. What this means, solve for c. Right, you actually get a value for c if you know this initial condition. So if I plug in 0, f of 0 equal to 0 to the 4th over 4 plus secant of 0 plus c, that's supposed to equal 8. Well, then I can solve for c. 0 to the 4th over 4, that's just 0. Secant of 0 is what? I don't hear any answers. So it is important to also to be able to evaluate trig functions. Did I feel like someone was about to raise their hand? Martha, you have a guess?
Yeah.
Is it
1?
What's that?
Is it 1?
It is definitely 1. So I will warn you, if you have your video up, I'm probably more likely to ask you something because I can see your face. I would love to see other people's faces. Also, I want to remind you all, I think I said this last class, but if I didn't, for those of you that don't want to put on video, that's perfectly fine. I would love for you to put up a picture. It can be of yourself. It can be of something you like. But a picture would be great just so it's a little more colorful at the top of the Canvas screen. So that's going to be 0 plus 1 plus c equals 8, meaning c equals 7. So for this specific question, our antiderivative would actually be, and then I'm kind of scrunched here, x to the 4th over 4 plus secant of x plus 7. So sometimes you have to solve for c if they give you an initial condition like that. All right, let's go to the other side of the board. I'm going to remind you, if you have a question and I'm not seeing it in the chat, just speak up. All right. So some rules that I'm sure we've seen already, but let me just say them again. So if your function is x to the n, then your antiderivative is x to the n plus 1 divided by n plus 1 plus c, as long as n doesn't equal what? What is n clearly not allowed to be?
0.
Negative.
So we can't
1.
divide by 0, which means n can't be negative 1. Exactly. So that actually kind of brings up the question. No, so just as some examples, right? If your function is, or if your derivative is x to the 16th power, then your antiderivative is x to the 17th divided by 17 plus c. And again, the whole reason this works is because if you differentiate that, you get back exactly this, right? I can take the derivative here. F prime of x is the derivative of x to the 17th over 17. I'm not going to use the quotient rule. I'm going to write this as a constant 1 over 17 times x to the 17th plus c. When you differentiate a constant times a function, you get the constant times the derivative of that function. What's the derivative of c? 0. So when you have a constant by itself, its derivative is 0. When you have a constant times a function, the derivative is the constant times the derivative of that function. So there's a bit of a difference there. And then these cancel and you just get x to the 16th. You don't need to do this work, right? You don't need to show that your derivative actually is what it's supposed to be, but it's good to see that, oh yeah, if I needed to, I could differentiate my antiderivative and get back to the function I started with. Okay. So another example, if f of x is, say, let's do this, x cubed plus x squared plus the square root of x, all divided by, sure, x. I want to find the antiderivative. Now here's the thing. There isn't really an anti-quotient rule. If you have a quotient or a fraction, or yeah, quotient's the better word, but if you have some sort of fractional function, the hope is that you can simplify it before antidifferentiating. And especially if you've got a quotient where the bottom thing is just one term, you can divide each thing by that one term. So I'm going to write this as x cubed divided by x plus x squared divided by x plus the square root of x is x to the 1/2 divided by x. And again, before I can antidifferentiate, right, I don't know how to antidifferentiate this like it is, right? I can't do x to the 4th over 4 divided by x squared over 2. You can't do it piece by piece and then smash it together. You have to simplify first. So this is going to look like x cubed divided by x, well, 3 minus 1 is 2, so I get x squared. 2 minus 1 is 1, so I get x to the first. And 1/2 minus 1 is negative 1/2, so I get x to the negative 1/2. And then I'm going to use the antiderivative rule. So I'm going to write capital F of x, and I'm just going to add 1 to the power and divide by the new power. So I'm going to get x to the 2 plus 1 over 2 plus 1, which is 3. I'm going to get x to the 1 there, so I get 1 plus 1 over 1 plus 1. And here I get x to the negative 1/2 plus 1 divided by negative 1/2 plus 1. Plus c. And if you're really not feeling like simplifying, you could leave your answer like this. I think you should simplify these ones. So we end up with x to the third over 3 plus x squared over 2. And now here, negative 1/2 plus 1 is positive 1/2. So I'm going to get x to the positive 1/2. And dividing by 1/2 is the same as multiplying by the reciprocal of 1/2, which is 2. So I'd really rather write this as 2 times x to the 1/2. Let's see. You could write it as x to the 1/2 divided by 1/2, but that just doesn't look, it's actually not simplified. And it doesn't look nice. So that's our answer there. Okay. So I just want to point out a few more basic antiderivatives, and then I think we will start moving in the direction of talking about more complicated antiderivatives, which involves u substitution. Now, I suppose I should ask, I know Merckx mentioned the fundamental theorem of calculus on the first day of class. Has he gotten back to talking about the fundamental theorem of calculus yet? He has? Like you guys have, I'm assuming you guys have talked about, I'm going to throw something up here, but don't worry if you haven't seen this yet. He's done stuff like the derivative of the integral of a of 2 to x of sine of t dt. Has he done something like that? No?
He just started introducing it. He's gonna get more to it in the next lecture.
But he has talked about u substitution already?
Yeah.
Okay. The order on that seems a little weird, but whatever. All right. We'll definitely talk about u substitution because u substitution isn't too terrible. So some antiderivatives you should already know. The first big one is if f of x, I wrote it on the previous, I'm gonna write it again. If f of x is x to the n, the antiderivative is x to the n plus 1 divided by n plus 1. Let's see. That's 1. Again, for n not equal to 1. Negative 1, sorry. We also have exponential functions. We know that if your function is e to the x, the antiderivative of e to the x is really nice. It's also e to the x. We also know some trig functions. In fact, there are six things we know. I know that if my function is cosine of x, I should really start with sine. The antiderivative is, what function has a derivative that's equal to sine of x? Well, a good guess would be cosine, but that's not exactly right. Because we know that the derivative of cosine of x is negative sine of x. So I need to have negative cosine of x, because the derivative of negative cosine is negative sine, which is sine. So the antiderivative of sine of x is negative cosine of x plus. In a similar way, the antiderivative of cosine of x is positive sine of x. Let's see. For me, the way I remember cosine and sine is that the derivatives and the antiderivatives have the opposite plus or minus. So if I know the derivative of sine is positive cosine, I know that the antiderivative of sine is negative cosine. I know that the derivative of cosine is negative sine. I know that the antiderivative of cosine is positive sine. It's always true for sine and cosine. You can also make this kind of list. So if you write like, so if I start with sine of x, what's the derivative of sine of x? Everybody.
Cosine.
Yeah, good. I would never unmute everybody. My coworker was telling me about a math class where the teacher did unmute everybody, and it was chaos. So the derivative of sine is cosine. What's the derivative of cosine?
Negative sine.
What's the derivative of negative sine?
Negative cosine.
And then what's the derivative of negative cosine?
Sine.
Exactly. So if we do the derivative 4 times, we get back to where we started, no matter where you start. And so here's the thing you can see if you want. You can see that going down the list gives you the derivative. Derivative of this is that, derivative of this is that, derivative of this is that, and so on. If you go up the list, you get the antiderivative. Where did my blue pen go? There's my blue pen. So if you go up the list, you get the antiderivative. You could use this symbol, the integral symbol, to represent that, although you might not talk about it yet in your class. Right? The antiderivative sign is negative cosine. The antiderivative of negative cosine is negative sine. The antiderivative of negative sine is positive cosine. The antiderivative of cosine is sine. So that's a kind of a nice, easy way to remember what's happening there. A couple more. We did one of these. So if your derivative, or if your function is secant x tangent x, your antiderivative is secant x. We don't know the antiderivative of just secant yet, or just tangent yet, but we will learn those eventually. Similarly, the antiderivative of cosecant x times cotangent x. So I know, and you hopefully know, the derivative of cosecant of x is negative cosecant of x times cotangent of x. So the antiderivative of cosecant of x times cotangent of x has to be negative cosecant of x plus c. Right, we need that negative there, so that we take the derivative of this. The derivative of this is negative cosecant of x times cotangent of x, which is positive cosecant of x times cotangent of x. Whew. Okay, the last two trig ones that we know right off the bat, and then really I'm just taking our derivative list and writing it backwards. I know that the derivative of tangent is secant squared, so I know that the antiderivative of secant squared of x is tangent of x. Let's see. And lastly, for the trig ones, I know the derivative of cotangent of x is negative cosecant squared. So I know that the antiderivative of cosecant squared is negative cotangent of x. Let's see. And no, I don't want to say that. So these are antiderivatives. No. Go ahead.
Sorry, I kind of had a general question.
Sure.
So when Merckx writes his problems, he uses the integral side. Does that mean like it's the antiderivative?
Depends. So let me answer that question. So let's go ahead. So I feel like I might be glossing over some things, and that's okay. But we definitely use the integral symbol for the antiderivative because it's easy, right? Like writing all this out is a pain to write it out that way. So here's what I'll say. There's a very natural reason to use the antiderivative, to use the integral symbol for the antiderivative. And the reason is because of the fundamental theorem of calculus, which I feel like has FAM's class started talking about the fundamental theorem of calculus? I feel like the answer is no.
No.
Okay, that's what I thought. So I feel like I don't want to go there just yet because it's kind of a big deal. Definitely next Tuesday we'll talk about the fundamental theorem of calculus for sure. Well, actually, let me back up. Okay, I'm going to state the fundamental theorem of calculus. You might not actually say the whole thing y. But there's two parts to the fundamental theorem of calculus. Part one, and I know I'm getting ahead of myself here, is that the integral from a to b of f of x dx, where this means, or one interpretation of this is the area under the curve f of x between x equal to a and x equal to b. So it looks like this. This is f of x, and that's a, and that's b. We're talking about this area here. There is a nice way of calculating this area. And the way you calculate this area is by anti-differentiating that and then plugging in b and a. So it's f gets the antiderivative of the function evaluated at the top value minus the antiderivative evaluated at the bottom value. I don't usually write it like this. I usually write it like this. The antiderivative of x, sorry, the antiderivative of f of x evaluated between a and b. Those are both perfectly good notations. I kind of like this one better. But in either way, you end up plugging in the values. And then there's the second part. The second part is really the thing we've already been saying. It just spelled out more explicitly. Here's what it says. The second part says the derivative of the antiderivative from some constant a to some variable x of some function is equal to the function. So let me say that again, because I know it might seem kind of weird. All this says is that the derivative and the antiderivative undo each other. If you anti-differentiate this function and then differentiate the result, you end up back where you're starting. Now I know it looks a little bit different because here I have f of t and here I have f of x. I wouldn't sweat that too much. It's really just because, well, I'll show you an example of this actually now. So I know I said I wasn't going to talk about the fundamental theorem, but here we are. So, sorry, I'm just trying to remember. There's a couple things I want to make sure I do in the next 20 minutes. Okay. So let's talk about an example of this, and then we'll talk about an example of this. Actually, sure. Okay. Actually, I'm going to go the other way. So, man, there's so many things to say. Okay. So back to your kind of original question. If I wanted to find the antiderivative of something, I might just write it like this. Like if I want to find the antiderivative of x cubed dx. So all these symbols mean for this indefinite integral. So this is an indefinite integral. And the thing that makes it indefinite is that there are no limits of integration, right? There's no bottom value and top value here. So when you see this without any limits of integration, it's an indefinite integral, which is the same thing. And that's what this symbol means. It means this is equivalent to. It's the same thing as finding the antiderivative of the function. And the reason, so let me back up one more step. The reason we use this notation to mean antiderivative is because if you're using the fundamental theorem of calculus to calculate the area under the curve, you're exactly using the antiderivative. So there's a very natural relationship between the antiderivative, capital F, and the integral. That's kind of the rationale behind using this notation for antidifferentiation. So if you see this means antidifferentiate, right? That's all these symbols mean. This big S symbol and this dx, these are just instructions that tell us to anti-differentiate. I don't think we actually need, why would I use quotes around there? Okay. All right. So what's the antiderivative of x cubed? It's x to the fourth over 4 plus c. Now notice when I anti-differentiate, I then lose those symbols, right? I don't write them anymore because I've done what the instructions have told me to do. It's kind of like how this notation, d dx of x to the fourth plus tangent of x, this is just instructions that say, this tells me to differentiate. So when I differentiate, oh, the derivative of this is 4x cubed plus secant squared x. But I no longer write this symbol because I've done what the instructions told me to do. I don't have to write down that I'm being told to do that anymore. All right, I want to contrast this with, and actually, sorry, I'm going to erase this here because I want to have this on the same page as this. So on the other hand, this tells me, so if I do the integral from, say, 1 to, no, let's not make it too terrible, James. Let's make it actually 0 to 4 of x cubed dx. These instructions now tell me, well, what this really means is find the area under the curve y equal to x cubed between x equal to 0 and x equal to 4. That's what that symbol says, or is telling me to do. Now, the way we do this still uses the antiderivative. So I end up with, well, the antiderivative of x cubed is still the same as it was before. It's still x to the fourth over 4. Now, I'm going to point out, when we do what's called a definite integral, actually this is a definite integral, which you should also just think of as we're finding the area under the curve. You don't need the plus c. I could write it. In fact, let's say I, yeah, sure, plus c. I'm going to erase it in a minute. It's this whole expression evaluated between 0 and 4. So whenever you're doing this, when you're doing the antiderivative evaluated between two values, you always plug in the top value first, and then subtract and plug in the bottom value second. So this is going to look like, and I'm running out of room here, it's going to look like, okay, if I plug in 4, I get 4 to the fourth over 4 plus c, minus, if I plug in 0, I get 0 to the fourth over 4 plus c. What do you notice about the c's? What's going to happen?
They cancel out.
Exactly. They always cancel out. Whatever this number is, whether it's 2 or 7 or a billion, you're always going to get one of them here and subtracting one of them there. And so we don't actually need to write them. We don't write them. So what this actually usually ends up looking like is you're just going to have, it's just going to be x to the fourth over 4 evaluated between 0 and 4. And we're not even going to write those. We're just going to write it as 4 to the fourth over 4 minus 0 to the fourth over 4. 4 to the fourth over 4 is 4 to the third, right? Subtract those powers. And 4 to the third. And then minus 0 to the fourth is 0. So you just get 0 there. So that ends up being 4 to the third, which is 64. And that tells me that for y equals x cubed, between 0 and 4, there are 64 square units of area under the curve. Let me draw the picture. Yeah, I might leave this up for just 1 second here. Actually, I'll just erase this. I might want that part there. So I'm not great at drawing x cubed, but it kind of looks like this. And so what we're saying, and I know my scale is not good. Fine. But I can use Desmos. Let's use Desmos. Desmos is fun and makes our graphs look nice. I know I've got a link here. Come on, computer. Sorry, just one sec. New window. There we go. So I'm gonna pull up Desmos real quick, and share my screen. So you guys actually want to see what's on my screen. Share my screen. Yeah, cool. Yes, do it. Take your time. Okay. So if I graph y equal to x cubed, right? I wonder if there's a way. I don't know if there's a way to like actually do the area under. But what I'm looking at here is I'm looking at. I got to 4. I want to go bigger. Wow, 64. Ooh, getting real big. Okay. So like here, right, I'd be looking at all the area under the curve from there to there, which I don't think I have a good way of doing. Nope, I want that back. Yeah, I don't know. I don't know Desmos well enough to actually know what to do, so oh well. But the idea here is, right, I'm just finding from 0 to 4, I'm finding all the area under that curve. It's exactly 64 square units. Whatever my units are, inches, feet, whatever. Sorry, let me get out of the screen sharing here. So that's the idea. Oh, I know what I want to say. So the takeaway here, the really, really, really important thing to make sure you're grasping is that if you have an indefinite integral, you're just finding the antiderivative, and your answer should be a function with a plus c. If you're finding a definite integral, where you have limits of integration, your answer should be an area, which should just be a real number. So those are the differences. Indefinite integral is an antiderivative. Your answer is a function of x usually. Definite integral, you're finding an area. Your answer is a number like 64 or pi or e, right? Any of those things that are just values. All right, let's go. So I think we're probably, unfortunately, not going to get to u substitution today. I'll try to make a couple of videos of some easy u substitutions for you guys. If there are specific examples you would like me to do, like there's an actual problem you have in mind, don't hesitate to send me an email or post a thread on, or a discussion thread on Canvas, and I will definitely try to make an example for that. But I wanted to mention this fundamental theorem of calculus because it's a little bit important. I mean, it's actually a lot important. It's super duper important, but this part of it is the part we probably use less. So it says the derivative of the antiderivative is equal to the function. So let's look at this example. Let's say I want to find the derivative of the antiderivative from, what constant do I want to use here? From say 2 to x of t to the, t to the third dt. And so, so what this part what the integral part here represents in red, this says it's the area under t cubed, which is the same as x cubed, but I'm using t because I'm using x there, between 2 and x. So what this looks like is, here's my cubic function. I'm going to make it look kind of dumb, just because, right, I want to make my graph look nice. Let's say here's 2, there's 8, and there's x, and there's x cubed. So what this part in red here is just the area under y equal to t cubed. My y-axis, this is my t-axis, because this is y equal to t cubed, between 2 and x. So I'm just saying it's that area there. But now here's the idea. That area is a function of x. A lot of times people will call this a of x, because it depends on the value of x. If x is larger, you're going to get more area. If x is smaller, you're going to get less area. If x was 2, you would get 0 area, because the area under the curve t cubed starting at 2 and ending at 2, you haven't done anything, you haven't gone anywhere, so you get no area. So that's actually an important thing to know as well. If your limits of integration are the same on the top and the bottom, you have exactly 0 area. Okay, so the way I would find this area using the evaluation theorem, which is just the part of the fundamental theorem of calculus we're just talking about, I'm going to have to erase this, yeah. So again, all I'm going to do is I'm going to anti-differentiate this. So this is going to equal, sorry, I'm not going to anti-differentiate. I mean, that's not all I'm going to do. I'm going to anti-differentiate and plug in my top value and my bottom value. So you guys hopefully all know by now, what's the antiderivative of t to the third? It's t to the
4 divided by 4.
Thank you, yes. And then I'm going to evaluate between 2 and x. So then I'm going to plug in my limits of integration. So I'm going to get the derivative of, first I plug in the top limit. You can get x to the 4th over 4. Then I plug in my bottom limit, and I get 2 to the 4th over 4. And I can simplify this a little bit. It's the derivative of x to the 4th over 4 minus 2 to the 4th is 16. 16 divided by 4 is 4. So here's what this tells me, just kind of before I differentiate. If I ignore the derivative part of this equation for a second, this tells me exactly how much area is under the curve for any value of x. Right? If x was 2, I would get 0 because I'd get 2 to the 4th over 4, which is 16 over 4, which is 4, minus 4. So if x is 2, the area is 0. If x is 3, the area, well, if I plug in 3, I get 81 over 4 minus 4. I don't actually care what that is. If I plug in 4, I get 4 to the 4th over 4, which is 64 minus 4, so I get 60. Right, so the bigger x is, the more area I get. But now here's the thing we actually care about. What's the derivative of x to the 4th over 4? Anybody?
Isn't it x to the 3rd?
Exactly. Or you could say it's 4x to the 3rd divided by 4, which is also x to the 3rd. What's the derivative of 4?
0.
Exactly. Sorry, you guys can see 0. So I end up getting x to the 3rd. Okay, now here's the really, really important thing to see. Well, actually 2 things. First of all, the derivative of the integral of this function is the same function. I'm just using a different letter, right? Here the function is f of t equals t cubed. Here the function is f of x equals x cubed. But it's essentially the same information. So the really, really, really important thing to see here is that the derivative of the antiderivative is equal to the function that we started with. I started with t cubed, I anti-differentiated, then I differentiated, and I got back to the same function. I just called it a different name. The other thing that's important to see here is it doesn't matter what this constant is. Right? This could have been 2, this could have been 3, this could have been 1,000. Whatever this constant is here, once I plug it in here, I'm just getting some number there. And the derivative of whatever that number is, since it's a constant, is always going to end up being just 0. So that's why it doesn't really matter what A is. Yeah, we got a few minutes here. So those are kind of the big takeaways here. The derivative of the antiderivative is equal to the original function. Let me show you 1 or 2 more quick examples of this. And again, this is the fundamental theorem of calculus, parts 1 and 2. Sometimes people call them 1, sometimes people interchange which part's 1 with parts 2. It doesn't really matter, but it does matter to know the 2 things. 1, the definite integral is just the area under the curve, and you find it by finding the antiderivative and plugging in the limits of integration. And the other part is that the derivative of the antiderivative is equal to the original function. So For example, I could ask you guys, what's the derivative of the integral from 7 to x of cosine of t dt? And you could certainly do it the long way. You could definitely anti-differentiate this, plug in your limit of integration, and then get your answer, and differentiate that. But you could also be like, oh, it's cosine of x. It's the same function that's in your integrand, right? That's called the integrand, the inner part of the integral, just with whatever the variable is up here instead of t. I could also go the long way. The long way would be say, okay, help me out, you guys. What's the antiderivative of cosine of t?
Negative sign of t.
You're almost right. That's the derivative is negative sign. The antiderivative is positive sign. So I get positive sine of t, but then I plug in x and I plug in 7, and I get the derivative of sine of x minus sine of 7. Maybe I didn't pick a great number with 7. What's sine of 7? I don't know, but here's what I do know. It's a constant. It's just some number, right? I could plug it into my calculator and be like, oh, sine of 7 is, where's my sine button? Sometimes sine, there we go. Sine of 7 is 0.12. Great. What's the derivative of 0.12? Oh, it's 0. So I get the derivative of sine, which is cosine, minus 0. And the point of this is you don't have to do all this work. You always just get to be like, oh, I'm differentiating the antiderivative of cosine, I get cosine. But it also works for functions that are too complicated to integrate or anti-differentiate. By the way, lots of people, and yeah, if you have to go, go ahead and go. I'm just going to say one more thing. Lots of people, myself included, often interchange the words anti-differentiate and integrate. So you should get used to hearing one and thinking of the other. They really go together. But for example, I can also do this for a function that's hard or impossible to integrate. For example, x cubed times, I should be using t, sorry. So the derivative of the integral from pi to t of x cubed times sine of x. Ooh, I messed it up, sorry. Apologies there. The integral from pi to x of t cubed times sine of t dt. This is not impossible to integrate, but it is very difficult to integrate. We'll learn how to later. But for now, I don't need to. I should say, oh, the derivative of the integral is just x cubed times sine of x. That's it. All I'm doing is I'm replacing my t's with whatever variable is up there. All right, that's all we've got for today. If you guys have questions or want me to see things, either start a discussion thread or, oh, the other thing, make sure you fill out the attendance form if you didn't fill it out already. Please do that. It is something we're gonna do every class, so make sure you do it every class. Send me questions. I'll post the videos that I just made before class shortly here, answering the questions that people had emailed me about before. I think that's it. Yeah, for those of you that have a quiz tomorrow, if you have questions about the quiz, I can also make little videos addressing those questions. But yeah, whatever you guys want, let me know and I will try to make it happen. All right, take care. For those of you in FAM's class, look at the thing I posted about the quiz. All right, I'll talk to y'all later. Bye.
Yeah.